Greetings, Mr. Colazar's class. What we're going to look into today is section 5-4, looking at spectroscopy and the atomic emission spectra. And what we're going to do is this is going to be kind of a lot of our kind of lab idea of the next couple days coming up. And we're going to look at matter can absorb and emit light at different frequencies and energies, and that can help us define what type of matter we actually have. So we're going to look at what the spectroscope is, and we're going to look at continuous and atomic emission spectra. So when we look at just white light for a second before we get into this, if you were to take just like sunlight coming in, there's an example of white light. If you have it go through a prism, you can actually separate that out into the different colors of light. And now a prism separates the continuous spectrum, or all the Roy G. Biv colors, if we were to see down below, all of the colors of light that we can visibly see. Now an atomic emission spectrum, if light of different matter is passed through a prism, an atomic emission spectrum is produced. And that's a set of unique frequencies and wavelengths emitted for each element. And it kind of acts like a fingerprint for identifying the elements. So an example would be, if we had hydrogen gas is being excited, and so it's producing some light as it passes through the atomic emission spectrum and through a prism, it separates out the light into visible light that we see, and that would actually be able to be visually shown which markers that light actually shows up on. So which wavelengths of light are actually being seen from this. Now, in your notes, it shows you that this is in nanometers. So when you look at that, nanometers, similar idea to meters, except we've got to change that a little bit. So 400 nanometers is going to be equal to 4 times 10 to the -7th meters. So use that information to calculate the frequency of one of the lines produced, and then calculate the energy. So this is just on your own. Complete this problem. Frequency, remember. And then for the second problem, energy is equal to. So use section 5.2 and 5.3. I'm going to move on. You're going to complete that problem. Now, what we're going to look at in lab are different ways to excite matter. So we have the flame test, where heat is used to energize matter. And then we have what are called our discharge tubes, where electricity is going to be used to energize matter. And as that matter gets excited, that energy is going to cause it to move up. So you're going to add energy, the electrons are going to move up, and then they are going to come back down, the electrons are, and they're going to release energy. And that energy they release is going to be in specific amounts unique to each element. We're going to use a spectroscope, a tool that as you look in and look at a material, you're going to be able to see it break down the light into specific wavelengths. And as we look at those wavelengths, you're going to be able to see different wavelengths or different actual markers of light identified unique to that specific element from the electrons being excited. So the two versions we're going to look at, the continuous electromagnetic spectrum has no gaps. It looks like a full continuous rainbow. So this would be an example. Sunlight would be an example of this. Where an atomic emission spectrum, also called an emission spectrum of an element, kind of looks like a barcode is a good way to look at it, where each element, like hydrogen, has 4 specific lines. Iron, a little more complicated, has a huge amount of spectral lines, but each of these are unique to an element for each element. So we can use those to identify what substance we have. Continuous spectrum, sunlight coming in, breaks down to all the Roy G. Biv. If we have a unique element, then we only have certain lines appearing. So that's the difference between those two as we look to them in lab.